Hello, welcome back to our continuing series, video series on the unification of physics. This is where we left off last time. We're pretty much done on this side of the ledger, the classical side. We discussed the general theory of relativity as our theory of gravity and basically our theory on large-scale physics. We also discussed last time Dirac's relativistic quantum mechanics. In previous videos, we had discussed the non-relativistic quantum mechanics. And if you remember, out of that came three wave functions. One of them was psi n, that dealt with the energy of the electrons around the nucleus of an atom. One of them was psi L, that dealt with the shape of the orbit. And then there was psi m sub s, the orientation of the orbit. But if you remember, we had to introduce by hand something called psi s, which had to do with the spin of the electron, before we could completely describe the way electrons were configured around the nucleus of an atom. When Dirac proposed his relativistic quantum mechanics, spin became a fundamental part of the quantum theory. There was no need to introduce extraneously a wave function for spin because it was incorporated as a unification of Einstein's special theory of relativity and non-relativistic quantum mechanics. It was four-dimensional, and it included all of this, whereas Schrödinger's equation was three-dimensional. So that was a leap forward. And again, it only applied to inertial reference frames. Dirac's theory did have some undesirable characteristics. For example, he had this quantum vacuum state that was all filled up with negative energy electrons. If we had a positive energy electron up here, it could give off energy in the form of radiation and become a negative energy electron. And there was nothing stopping it from doing that. In order to explain the existence of positive energy electrons, Dirac imagined this quantum vacuum state that was completely filled with negative energy electrons. And because electrons were fermions, they couldn't occupy the same quantum state at the same time. And so if this vacuum state was completely filled with negative energy electrons, the positive energy electrons couldn't occupy these states. Dirac's theory also led to the discovery of the positron, the anti-electron. But in his theory, when a negative energy electron happened to pop into the positive arena and leave a positively charged hole in the vacuum, Dirac's concept of a positron was the absence of a particle rather than a particle itself. Later on, when quantum field theory was developed, the positron became a particle rather than the absence of a particle. So some of the issues associated with the quantum vacuum were resolved by quantum field theory, but not everything. There's still problems within quantum field theory in that the vacuum now has infinite energy, and we have to use renormalization to get rid of it. Today, we're going to add a new bullet, and it's going to deal with the nucleus of an atom. Nucleus. It turns out that Dirac's theory completely describes how the electrons move around, but there's no theory yet, or no theories, or any kinds of ideas about the characteristics of the nucleus. And so that's what we're going to discuss today. This is, of course, where we want to get to. We've finished our discussions on the classical side, but on the quantum side, we really haven't arrived where we need to get to. We want to get to a discussion of the standard model. We haven't quite got there yet. We're going to discuss theories that cover the nucleus of an atom in this video, and then in the next video, we will discuss the standard model. And of course, if you remember, these are the two great theories of the 20th century, the general theory of relativity and the standard model, and that they are incompatible. They're two different kinds of theories based on two different foundational approaches. And what we would really like to do in the 21st century is find a way of uniting the two. And the name for that unification is quantum gravity. Doesn't exist yet, but that's where we would like to see physics head, and that's called the unification of physics. So let's get started on discussing the theories that cover the nucleus. So at this point in time, the constituents of the atom were basically the electron and the proton. The proton made up the core of the atom, the nucleus of the atom, and the electrons were configured around. Back then, that's what people hypothesized the atom to be made up of. Now, there was a couple of issues concerning the nucleus. One was size. Why weren't the same elements the same size? For example, there were elements of hydrogen that weren't the same size. So that was one issue. The other issue was the stability of the nucleus. First was size. How come the nucleus didn't blow up and just become infinitely big? How come you didn't see elements with a bigger core than you did? The second issue was, why didn't the nucleus just fly apart? The nucleus was made up with a conglomeration of protons, and Coulomb's law predicted that like charges would repel what was holding it together. The first issue that we will address is the size of the nucleus. And the first theory put forward was that some of the protons in the nucleus of an atom contained an electron. So, for example, nitrogen-14 was thought to have in the nucleus 14 protons and 7 electrons. There was a couple of issues with this particular hypothesis. One, the theory that supported this predicted more spectral lines in the hydrogen atom, or different spectral lines than what they actually observed. So that was one problem. And the other problem is that the spin characteristics of the nucleus of the atom contradicted Dirac's theory. Eventually, this nuclear electron hypothesis that was first advanced was given up. It was abandoned. And the thing that really led to a resolution of this issue was an experiment that was conducted by a couple of German physicists, Botha and Becker. They took a source of plutonium because it's radioactive. It emits alpha particles, and the physicists back then were familiar with nuclear decay, what we call radiation or radioactivity. There were 3 kinds that were known at the time. The first was alpha decay. They aren't given very imaginative names. The second was, you guessed it, beta decay, and the third was gamma decay. And those were the 3 types of radioactive decays that were known at the time. And so they could simulate radioactive decay in the laboratory and do experiments and make hypotheses and try to figure out what was going on. The source was highly radioactive, emitted alpha particles, and alpha particles have a +2 electric charge. They shot these alpha particles at beryllium, a very light source, and what they detected was radiation that was neutral. They put it in an electric field, and it didn't react. And they wanted to know what this neutral radiation was. And so it slammed into paraffin, knocked the protons out of the paraffin, and those protons passed into a Geiger counter, and the Geiger counter could measure the energy of the protons. And so the whole idea was to try to figure out what this neutral radiation was. Well, how did they know it was neutral? Well, they put it into an electric field, and it didn't react. So they knew it couldn't be alpha decay, because alpha particles would have an electric charge, and therefore it should have reacted to it being placed in an electric field, and it didn't. The other decay that was known at the time was beta decay, but that emitted electrons, which are also charged particles. So if you put this radiation into an electric field, it should have been affected by it, and it wasn't. So they had eliminated these 2 types of radioactive decay as possibilities. However, gamma decay was neutral. Gamma rays were not charged. The 2 physicists hypothesized that these were gamma rays, but the energy of the protons that were emitted from the paraffin into the Geiger counter was too high if this radiation was gamma rays. Gamma rays didn't have enough energy to create the energy that these protons were registering. James Chadwick, a British physicist, he hypothesized there was a new particle. He wrote a paper on this, and when he gave the spin characteristics and size that he hypothesized, it was immediately clear that he had discovered something new. And of course, eventually became known as neutron. So now the atom consisted of the electron, the proton, and the neutron. And that gave an explanation for why elements had different sizes. The next issue that arose regarding the nucleus of an atom was stability of the nucleus. How did it stay together? And there were lots of theories that were advanced to explain this, but the one that's gained the most popularity was the theory advanced by Hideki Yuikawa. He was a Japanese physicist, unknown at the time that he did this. He put this theory forward in about 1935, and it became the precursor to the gauge theories that eventually made it into the Standard Model. And that's why it lasts in history. It's very important because of the concepts it used. And what Yuikawa proposed was that in the nucleus of an atom, there was more than protons and neutrons. There was something called pi mesons. This was a negative pi meson, and that the nucleus of an atom wasn't this stable conglomeration of protons and neutrons. Protons and neutrons change identities. A neutron that emitted a pi meson, a negative pi meson, turned itself into a proton, and a proton that absorbed a negative pi meson turned into a neutron. The nucleus of an atom was constantly changing its makeup by turning protons into neutrons and neutrons into protons. And this created attractive forces, and it was what held the protons and neutrons together. He showed that how this could take place within the nucleus. Physicists were a little suspicious about his theory. For one thing, if these pi mesons existed and they were not massless particles and they exchanged and caused all these changes in the identities of these particles, why were protons and neutrons never found with other than their normal masses? And so this was a question that he had to answer. And he did it in kind of an ingenious way. He said that the pi mesons only exist for a very short period of time, but they had to be associated with a certain amount of energy in order to hold these particles together. He had to predict the range of this force. And the way he did that was to use the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle really says that you can borrow energy, but you have to pay it back. What Yuikawa proposed was that this exchange of mesons occurred within the constraints of the uncertainty principle, and therefore it didn't violate the conservation of energy. Here's sort of how he did that. If you'll remember, distance can be related to time by the equation d, they'll say is the distance, that's equal to v times t. And if v is equal to c, then we can write this as d equals c times t. And if we set c equal to 1, since c is a constant, then distance really becomes time. So the range of this force can be expressed in the amount of time that the particle that he called a pi meson lasts. Let's see how he did this. If we estimate the time that this pi meson, if it's traveling near the speed of light, we can estimate the time that it lives by d, that's the distance, divided by c, the velocity. The distance, it was thought that the range of the force was about 10 to the minus 15th meters, which was about the size of a nucleon. And then if we divide that by the speed of light, which is approximately 3 times 10 to the 8th meters per second. That comes out to be about 3 times 10 to the 24th seconds. I'm running out of room here, but that's seconds. So that's not very long. 3 times 10 to the minus 24 seconds. Sorry. If we plug that into the Heisenberg uncertainty equation that's generally written in terms of energy and time, this is equal to Planck's constant over 4 pi. We can rewrite this. The energy then is equal to h divided by 4 pi times delta t. If we plug the numbers in here, that's going to give us an energy of about 6.6 times 10 to the minus 34, 4 pi, times, for delta t, we plug in 3 times 10 to the minus 24. Now, this calculation turns out to be, and I won't go through the conversion factors here, about 100 milli-electron volts. And if we use the equation E equals mc squared, then that implies that m is equal to E over c squared, which implies that m is equal to 100 milli-electron volts divided by c squared. And that mass there is about 200 times the size of an electron. And so he was able to predict the mass of this pi meson. This was confirmed experimentally. I won't go into the details of how that was done, but the mesons that were discovered, there was a pi zero meson, a pi negative, and a pi positive, and these were all around 135 milli-electron volts per c squared. And so that was a pretty good estimate. This 100 milli-electron was a pretty good estimate of what was experimentally observed. That gave Yuikawa's theory credibility because he pretty much correctly predicted the mass of the pi mesons that would be exchanged within the nucleus, and it became the precursor of the gauge theories that eventually made it into the Standard Model because of this idea of particles exchanging what became known as gauge bosons. Those were force-carrying particles that allowed the protons to be held together in the nucleus, and this was the theory that predated all the more modern theories that we find in the Standard Model today. So the next issue, why couldn't the nucleus of an atom be infinitely big? This is generally explained through the idea of nuclear decay. All physical systems seem to move from a excited state or a more energetic state to a less energetic state. Again, there are 3 types of nuclear decay, alpha, beta, and gamma. We've talked a little bit about that before. We're going to talk about alpha decay in this particular segment of the video. Alpha decay is basically a radioactive decay where the nucleus of an atom emits an alpha particle, and an alpha particle is defined as the nucleus of a helium atom, where there are 2 protons and 2 neutrons. Here we have an example. This is uranium-238. It has 92 protons, I think. It emits an alpha particle. It changes into a nucleus that has 234 particles, 90 protons. And it goes from here to here by emitting an alpha particle. Way this is explained, and the guy who first gave an explanation for this type of decay, his name was George Gamow. He was sort of famous in showing the superiority of quantum mechanical concepts over classical concepts by conceiving this decay as though the particle existed in a well. The particle would bounce around. The classical theory predicted that it would never be able to go out of of the well, because potential energy, which is represented by this dotted line here, that's the maximum energy that this particle that's bouncing around in here could achieve. And so if it's in this well, it could never escape because it just didn't have enough energy. But in quantum mechanical terms, this became just an average. It wasn't something that couldn't be exceeded. This was the average energy of the particle that was bouncing around. But since this was an average, some of the time the particle could gain a little more energy, sometimes less. Very occasionally, the particle will have enough energy to bounce outside the well. And that was what happens basically here, is that when the nucleus gets to, about 210 neutrons and protons, the probability that alpha decay will occur becomes higher. It's because the electrostatic force gets to the point where it's overcoming the short-range nuclear forces Iwakawa predicted. So when it gets too big, Coulomb's law begins to overcome Iwakawa's law, and what you experience is alpha decay. And so Gamow had explained how this could occur using this well concept. Gamow was able to show that his well principle correctly predicted the half-lives of certain atoms. That was sort of a spectacular demonstration of the superiority of quantum concepts versus classical concepts. The next type is beta decay. There's beta minus and beta plus. In beta minus decay, the number of neutrons is decreased and the number of protons is increased, and there is an expulsion from the nucleus of an electron. And beta plus decay, the number of neutrons is increased and the number of protons is decreased, and expelled from the nucleus is a positron. Now, there was a couple of things about beta decay that didn't make any sense when it was first discovered. For one, when did beta decay occur? It's a quantum mechanical phenomenon in the sense that it's very difficult to predict when beta decay will occur. But roughly speaking, when the ratio of neutrons to protons gets much above 1, then the likelihood that beta decay will occur goes up. And that's sort of a rule of thumb. It's not something that's certain. There were a couple of other things about beta decay that were mysterious. For one thing, if an electron was emitted, there wasn't supposed to be electrons in the nucleus of an atom. But where did this electron come from? And that was explained was kind of a sleight of hand, where the electron is conceived as being created immediately upon leaving the nucleus. The other thing that was mysterious is that when beta decay was first discovered, it seemed to violate conservation of linear momentum and the conservation of energy. So nobody could really understand why beta decay occurred if it couldn't be explained in terms of the conservation laws. And it was Wolfgang Pauli who hypothesized that if you included another particle that had small or zero mass, then the problems with the conservation laws would go away. This new particle was entirely hypothetical. It had never been discovered in a lab. In fact, the neutrino wasn't discovered until 1959. That was much later than what we're talking about here. And the reason it was hard to detect this particle was because it interacts very weakly with matter. A neutrino doesn't have electric charge. It doesn't interact electrically with matter. And its mass is so small that it has to go through about 130 light years of solid lead on average before it will interact with matter. The hypothesis is that you have millions of these neutrinos passing through your body every day. You don't know it because those neutrinos do not interact with anything in your body. This was a hypothetical particle invented to explain why the conservation of energy laws weren't violated. But in 1959, they did discover the neutrino. This explained why the conservation laws weren't violated in beta decay. So the next kind of decay, gamma decay, is really a result of other decays. alpha decay and beta decay. What happens in alpha decay and beta decay is the nucleus of the atom is left in an excited state. What that means is that it vibrates. As we said before, atoms tend to go from an excited state to their lowest energy state. It just seems to be a law of the universe. When the nucleus is in an excited state, because of the recoil energies that are in other types of decay, it moves to a lower state by emitting gamma rays. Okay, those are the three types of decays. Here's what we've covered so far. On the left side of the ledger, classical physics, we've talked about Newtonian mechanics and its concepts of space-time and matter. We've discussed Maxwell's electromagnetism. It's a field theory. We've discussed Einstein's theory of special relativity, which removed the contradictions between Newtonian mechanics and Maxwell's theory by unifying space with time. They only applied to observers in inertial reference frames. And then we talked about the general theory of relativity, which is our current theory of gravity, and it's also a field theory. On this side of the ledger, we've talked about non-relativistic quantum mechanics. It's a three-dimensional theory. It was replaced by Dirac's relativistic quantum mechanics. It's a four-dimensional theory. It explains the spin states of electrons and other particles by uniting special relativity with non-relativistic quantum mechanics. Again, it applies only to inertial reference frames, but it has this unusual characteristic of the quantum vacuum that was somewhat unsatisfactory, and it took the development of quantum field theory in order to address some of the issues associated with the quantum vacuum. In this video, we covered the nucleus of an atom. There was the discovery of the neutron, and that explained why elements came in different sizes. Why didn't the atom fly apart was explained by Yukawa's theory. And then we discussed nuclear decay, explained by three theories: alpha decay, beta decay, and gamma decay. All these theories explain aspects of the atom, but we really didn't have a theory of elementary particles. And that's what we want to get to. We have Dirac's theory that explains the configuration of electrons around the nucleus of an atom. We have a theory that explains what goes on inside the nucleus of an atom. But we really needed a theory of elementary particles. There were a lot more particles that existed than just those associated with the atom. We really needed a theory of elementary particles. That theory became known as the Standard Model of Particle Physics, and it's what we're going to discuss in the next video. So just as a reminder, this is where we're trying to get to. Again, in the next video, we're going to talk about the standard model of particle physics, complete our journey on this side of the ledger. We've already completed this side of the ledger, the classical side. We have developed a general theory of relativity. It's our theory of gravity. It constitutes physics on the large scale. In the next video, we'll complete our discussion with an assessment of the Standard Model of Particle Physics. It basically generates three theories: electrodynamics, weak interactions, and the strong force describes how the nucleus of an atom stays together. It really is our theory of small-scale physics. If you want to know about the Standard Model of Particle Physics, please tune in.